So, welcome to today's lecture on elliptic curves cryptography. So, in continuing with public key ciphers, today we shall discuss about a special type of cryptographic technique, which actually is based upon geometrical interpretations. So, it is a classic combination of algebraic properties with geometric techniques. So, we shall discuss about two fundamental elliptic curve arithmetic operations, namely point addition and point doubling, and then discuss about some of the forms of elliptic curve equations which are used in cryptography, and then discuss about projective coordinates which are often useful for implementing elliptic curves. To start with, let us start with a puzzle. That is, let us consider this question, that is, what is the number of balls that may be piled up as a square pyramid and also rearranged into a square array. So, this problem is a kind of a seemingly simple problem which can be solved easily in this fashion. That is, let us assume that x be the height of the pyramid. So, if we assume that x is the height of the pyramid, then so we can essentially try to compute the total number of balls in this fashion. So, for example, if you consider that your pyramid is arranged in various squares and you start on building up the pyramid, then you can count the number of balls in this fashion, right. So, you can count, you can imagine that the pyramid is made of squares of balls, okay, and suppose this is the height of the pyramid, and the height of the pyramid is denoted in this case by x, okay. So, what is the total number of balls in the first layer? It is 1 by 1, so it is 1 square. So, there are 1 square number of balls. In the second layer, it is 2 square number of balls. So, if I continue like this, the last layer has got x square number of balls. So, therefore, total number of balls can be computed in this fashion as 1 square plus 2 square plus so on till x square. Now, these balls by the question can also be rearranged into a square array. Okay. So, we can actually take these balls and rearrange them in the form of a square. So, the square also has a dimension of y by y, and therefore, the total number of balls can also be written to be equal to y square. So, if we solve these two equations, then therefore, we know that the left hand side computes to x into x plus 1 into 2x plus 1 by 6, and that is equal to y square. Now, this form of equations is referred to as the elliptic curves. Okay, so, it may be remembered at this point that its name actually derives from the word from the terms in elliptic integrals, and it has got nothing to do with ellipses. Okay. So, therefore, if we solve or rather write or rather draw this kind of this graph, then the graph would look like this. So, therefore, we can actually obtain certain we can observe certain properties. For example, it is symmetric over the x axis, and there are two distinct lobes here. Okay. So, this is a kind of form of these kind of curves which are commonly known as elliptic curves. So, these are cubic curves in the variable x, and they are also symmetric about the y axis. So, this is a kind of distinct property, and clearly we see that it has got no similarity with ellipses. So, therefore, it should not be mistaken that elliptic curves have got any similarity with ellipses. So, now there was a famous method which is known as the method of Diophantus, which is often used to it uses a set of known points to actually produce new points. For example, from this graph immediately we know that there are two trivial solutions, like for example 0, 0 satisfies this equation. Similarly, 1, 1 also satisfies this equation. It can be easily seen, like if I substitute 0 and 0 on both sides, it is satisfied. If we substitute 1, 1, then the left hand side computes into 1 into 2 into 3, that is 6 divided by 6, and the right hand side also 1 square satisfies this equation. Now, starting from these two trivial roots like 0 and 0 and 1, 1, Diophantus methods gives us new non-trivial values which will satisfy this curve equation. So, how does it work? It is like this. So, the technique is like this, that is, we take a line through these points, like we take 0, 0 and 1, 1, and we draw a line which connects 0, 0 and 1, 1. So, it is easily understood that the equation of the line through these points is y equal to x. So, now let us take this y equal to x and find out where does this line intersect the elliptic curve. Because since it is a cubic curve in x, it can be easily seen that if I take 2 points on the curve and draw a line, then it should definitely meet the curve on a third point. Okay. So, therefore, let us try to find out that equation or that coordinates of the third point, and it can be found out by substituting y equal to x into the curve, and the curve therefore takes the form of x cube minus 3 by 2 x squared plus x by 2. It can be checked, and that is equal to 0. So, now we would like to find out the roots for this equation to obtain the x axis of the third point, third intersecting point. So, what we have done is essentially like this. We have taken, suppose this is the curve equation, we start with this point 0 0, we start with the point, we take the other point, that is 1 1, and we draw a line through these 2 points, and it is believed therefore, since it is a cubic curve in x, this should definitely intersect the curve again at another point, and we are trying to find out the x coordinate of that point. Okay. So, if we do so, that is, if we substitute this, then we see that we get this equation x cube minus 3 by 2 x squared plus x by 2 is equal to 0. So, therefore, what we have done is that we have taken this y equal to x equation of the line and substituted it into the equation of the curve, which is given by this. So, basically, we are trying to solve simultaneously y equal to x and the equation of the curve. Now, we know from the theory of equations that since we know that this equation has got 3 roots, out of them 2 of them has got a value of 0 and 1. So, that means 0 plus 1 plus the third point which we are trying to find out, let us call it x, this should add up to the value of 3 by 2, right, because that follows from the theory of equations, that if we sum up the all the roots, then it is the negative of the first coefficient, which is here in this case minus 3 by 2, and therefore, this is equal to plus 3 by 2. So, therefore, from this we get that x is nothing but equal to half. Okay. So, therefore, what is the value of y? Since it lies also on the x equal to y line or y equal to x line, therefore, y is also equal to half, right. So, therefore, we obtain another point which is half comma half. Right. So, that means now this is a third point on the curve, and it is a more kind of, we can say it is a more non-trivial root than the roots that with which we started with. Okay. Now, immediately we know that if half comma half is a point on the curve, then by the symmetricity of the curve, half comma minus half is also a point on the curve, right. So, that means that we know that if half and half are points on the curve, then by the symmetricity of the curve, half comma minus half is also a point in the curve. So, now we shall try to find out, that is, what is the line which joins half comma minus half and 1 comma 1. Okay. So, we will again similarly continue this approach, and we will obtain further and further points. So, our objective is to obtain further and further points and ensure that the value of x is an integral value, because if we obtain a value of x which is the integral value, then that gives us a non-trivial solution to the puzzle that we started with, right. So, therefore, what we do is that we take this half and minus half and we draw a line through half minus half and 1 comma 1. Okay. So, we already knew that 1 comma 1 is a point, we have got a half minus half point, we want further points. Okay. So, what we do is that we take these 2 points and we draw a line, and if we can easily check that the line which joins 1 comma 1 and half comma 1 minus half, we will have the equation of y equal to 3x minus 2. Okay. So, this is quite trivial, I am not going into this, but we can obtain the equation of the straight line in this fashion. Now, we will intersect this with the curve again, that is, we will substitute y equal to 3x minus 2 into the original curve equation, and we obtain an equation in that case which has the form of this. So, we are not actually bothered about the higher terms, because what we need is the is the value of this, right, because we need to find out the value of x. So, we know that one value is 1, the other value is half. So, that means 1 plus half plus x should give us 51 by 2. So, this means that the value of x in this case comes out to 24. Okay. And if you substitute this value of x into the equation, we obtain the value of y as 70. So, that means that we remember that in our case this gives the height of the square pyramid and this gives the dimension of the square arrangement of the ball. So, that is what is the number of balls, therefore the total number of balls is therefore in this case 70 square, or that is 4900, right. Anyway, this is not so important in the perspective of cryptography, but what is important is that using this technique of Diophantous you can produce more and more number of points on the elliptic curve, right, and this technique is actually employed in computing arithmetic or performing arithmetic on the elliptic curve points, that is point addition and point doubling, which we will soon see. That is the same technique is still being adopted for elliptic curve operations. So, therefore, now we come into the application of elliptic curve, or rather talk about elliptic curves in the context of cryptography. So, this was essentially first proposed or first found in the literature on cryptography, and in around 1985 developed independently by Neil Koblish and Victor Miller. And the fundamental problem on which elliptic curve cryptography is based is commonly known as the discrete logarithm problem. Like what we have seen is discrete logarithm problems on finite fields in the last class. Similarly, we can actually develop discrete logarithm problem on elliptic curve groups, and it is believed to be more difficult than the corresponding problem in the underlying finite fields, and that actually leads to a significant importance in cryptography, because this reduces the sizes of the operations which you are doing it, and therefore elliptic curve cryptography is probably the most efficient public key ciphers, at least one of the most efficient public key ciphers that we have seen, okay, and therefore it is quite important. So, first of all, let us try to see some elliptic curves, or let us try to conceptualize how elliptic curve looks like. So, consider this field of modulo 5, okay, that is we will consider the x field to lie within modulo 5, x and y values to lie within modulo 5. That means it can take the value of 0, 1, 2, 3, 4, and that is it. So, that means now let us start with some points like x equal to 0. So, immediately if I substitute y square equal to 3, I see that in modulo 5 there is no solution. That is, if I take the value of say 0, 1, 2, 3, 4, then if I square them, none of them will be equal to 3. Okay. So, that means there are no solutions for this. Consider x equal to 1, if you substitute this you get x square equal to 6, and therefore modulo 5 this is 1. Immediately you know that both 1 and 4 are solutions, because you know that 1 squared is 1 and 4 squared is 16, modulo 5 is again 1. So, therefore, these are solutions. Similarly, you can obtain the other solutions, and what you find is that therefore, the points on the elliptic curves are actually 1, 1, 1, 4, 2, 0, 3, 1, 3, 4 and 4, 0. So, let us now not consider this point in infinity, which I will define later on, but actually we can say that these are some discrete points on the elliptic curve. Now, the reason why we are actually considering this example is to understand that although we are actually drawing continuous elliptic curves, they are actually not continuous, but they are discrete curves. That is, the curves are actually defined on certain finite elements. That is, they are not actually continuous curves, but they are actually discrete collection of points. So, using the finite field, we can actually form elliptic curve groups where we have got an elliptic curve discrete log problems, which is often commonly called as the elliptic curve discrete logarithm problem, but I will define that later on. But first of all, let us at least try to understand that elliptic curves on a finite set of integers are actually a cluster of discrete points and not continuous points. So, a definition of elliptic curve would look like this, that is, an elliptic curve is defined generally over a field k, like what we have seen in the previous example. It was defined over the points on it was defined over the points on the modulo 5 field, right. So, similarly, it is always defined over a field k, and it is a non-singular cubic curve. It is non-singular. I will define what is meant by non-singular, but it is non-singular cubic curve. It is cubic curve in x, and it is generally in two variables f(x, y) is equal to 0 with a rational point. So, there is an additional point which is called as a point at infinity. Now, what is the purpose or what is the definition of the point at infinity, we will see soon. The field K is usually taken to be the complex numbers, real numbers, rationals, algebraic extensions of rationals, periodic numbers, or generally a finite field. Okay. So, it can be various kind of various kind of algebra which I mean based upon which the field K can be defined. So, elliptic curve groups for cryptography are examined generally with underlying fields on Fp. So, it is Fp means it is a prime field where p is greater than 3 and it is a prime, or it is a binary extension where there are 2 power of m element, that is f 2 power of m fields. So, generally whenever elliptic curves are applied for cryptography, then the underlying fields are either in Fp or in f 2 power of m. So, consider this is a very common general form of the elliptic curve equation, which is like this, that is y square equal to x cube plus ax plus b. So, here this is a plane curve which is defined by an equation of the form y square equal to x cube plus ax plus b. Now, note that x here is again not a discrete point, I mean it is not a continuous point, but it is chosen from a particular field. So, it is either chosen from maybe GFP, where it is all prime numbers like 0 to p minus 1 for a large prime number, or it is GF 2 power of m, that is where the numbers of the elements can be expressed in certain discrete points again. Okay. So, that is chosen from what is known as the binary fields. So, similar to that, we can actually, like what we have seen previously, we can actually imagine these curves, and these are some common ways of denoting this. Although again note that we have drawn continuous curve equations or continuous curve diagrams, they are actually not continuous again, they are again some discrete points which have been joined. So, for example, consider this like y square equal to x cube minus 1, y square equal to x cube plus 1, and there are some several points which have been, several graphs which have been drawn. So, what is important here is that this graph is a cubic curve in terms of x, and also this graph or curve needs to be non-singular, which means that we have to ensure that the del f of del x and the del f of del y are not the same and equal to 0, which means that the graph should generally have should not have double roots in it. Okay. So, we will see more of that in our future discussions. Now, a common or more generalized form of this elliptic curve equation is what is referred to as the Weierstrass equation. Now, it is a two variable equation f(x, y) equal to 0, which forms a curve in the plane. Okay, and the generalized Weierstrass equation of elliptic curves looks like this, that is y square plus a1 xy plus a3 y equal to x cube plus a2 x square plus a4 x plus a6. So, here you know we may note that again the cubic order is again maintained, that is x is again having an order, a term of x cube, okay, and the term y has got a power of y square. So, this is very important and fundamental to the definition of elliptic curves. So, here x and y and constants all belong to a field again of say rational numbers, complex numbers, finite fields Fp or Galois field Gf 2 power of n. For cryptography, generally we choose them again from the finite fields or from Gf 2 power of n. Now, this Weierstrass equation, depending upon the characteristic of the field, okay, actually takes various forms. So, the characteristic of a field is actually like if I take an element say 1 and if I add them say lambda number of times, if I get 0 and that lambda is the minimum number of times when you have added, that is commonly referred to as the characteristic of the field. For Gf2 fields, the characteristic is 2. Like if I take 1 and I add 1, I get 0. That is the minimum number of times I need to repeatedly add 1 to get a 0 in the binary fields. So, depending upon the field characteristic, its curve equation varies. So, for example, here what we have done is that we have taken the original Weierstrass equation and we have tried to kind of manipulate them using the fact that the characteristic field is actually not 2. So, what we have done is that we have started with this original Weierstrass equation, which was like y square plus a1 xy plus a3y equal to x cube plus a2 x square plus a4 x plus a6. So, what we are now doing is that we are using the fact that the characteristic of the field is not 2, and using that we are trying to manipulate this and write it in this form like y plus a1 x by 2 plus a3 by 2 whole square equal to x cube plus a2 plus a1 square by 4 x square plus a4 x plus a3 square by 4 plus a6. So, it may be noted that what we have done is that we have actually expressed this in this form. So, if I simplify this, again this original equation will be obtained. Now, you note that since the characteristic of the field is assumed not to be 2, therefore, we can actually divide with the number 2, okay, that is important. So, therefore, if I do so, then we can see that this particular term here, that is y plus a1 x by 2 plus a3 by 2, can now be replaced by a single variable. Okay. For example, I can replace this by a variable say y, and I can call it like y square equal to x cube plus I call it like a2 dash x square plus a4 dash x plus a6 dash. Okay. So, therefore, this is the same Weierstrass equation, but written in a more simpler way, assuming the fact that the characteristic of the field is not 2.
a1 x by 2.
Yeah.
Y plus a1 x by 2.
Y plus a1 x by 2. So, we have actually substituted the entire thing by y. Okay. So, you can basically the entire thing is being substituted by y here. Yeah, that is why when you take this 2, then you have got a1 xy term here, right. So, therefore, the entire thing is now being replaced by y here. Okay. Now, similarly, you can actually continue simplify it in further way. So, what you can do is that you can assume now that the characteristic is neither 2 nor 3. So, if you assume that, then you can make further substitutions, like you can, since if you assume that in this case we assume that the characteristic is not equal to 2, we make further assumptions like the characteristic is not 3, and therefore, we can substitute like x1 is x plus a2 or rather a2 dash by 3. So, if you do that, then this further reduces to the form of y square equal to x. So, I am just little bit abusing the notations, but the basic form that it will be reduced to is this. Okay. And this is a very common form of the cubic curves, that is, we know that it is neither a characteristic 2 field or neither a characteristic 3 field, in which you can actually, I mean, under which assumptions you can rewrite the curve equation in this simple form. So, therefore, you can actually start with the original generalized Weierstrass equation, and you can actually rewrite them depending upon the characteristic of the field. Okay, you can actually make it more simple and you can write them, right. So, therefore, now what are the points on the elliptic curve can actually be written in a more formal way. You can say that the points on the elliptic curves, say call it an elliptic curve E, which is defined over a field L, to be the collection or the union of a point at infinity and the ordered pairs of x comma y, which belongs to L cross L, because x also belongs to L and y also belongs to L. So, therefore, it is a subset of the L cross L, the Cartesian of L and L, right, and all of them, I mean both x and y, satisfies the original curve equation, where there are definitely these two things like y square and the x cube terms. The rest of the things may vary depending upon the characteristic of the curve. So, it is useful to add the point at infinity, and we will see more closely why. The point is sitting, this point at infinity is a kind of point which is generally believed like it is sitting at both the top of the y axis and also bottom. So, therefore, it lies kind of at both the spaces. So, therefore, for example, if I draw a point or rather draw an elliptic curve, an elliptic curve would essentially look like this, and it will be encompassed with various points which lie on the curve, but we assume that there is a point which is both at the top and both at the end, and this point is also commonly known as the O point, okay, or the point at infinity. Okay. The same point, this point O is also at the top. So, therefore, if I draw a vertical line, then we know that by the original Diophantous technique, what we are seeing is that if there are 2 points and if I draw a vertical line, then it should also intersect the elliptic curve again at a third point, right. But in this case, since it will not actually intersect on the elliptic curve, we assume that it intersects the elliptic curve again at a point at infinity, okay, and that is the concept of the point O. So, therefore, it is both at the top and at the bottom of the y axis, and any line is said to pass through this point when it is vertical. Okay. So, any vertical line will intersect this point at infinity, which is also assumed to lie on the elliptic curve based on this definition. Okay. And it is a very useful point, because it helps us to define the concept of a group, okay, because it helps us to create a group which is very much needed in order to apply this elliptic curve for various applications, right. So, let us see some of the reasons why the elliptic curve should form an abelian group. Now, this is slightly a recapitulation of the abelian group. We know that given 2 points P and Q, which lies say in E of Fp, so it is an elliptic curve which is defined over the say finite say on the prime fields. Then there is a third point which is denoted by P plus Q, which also lies on E of Fp. That is, if I take P and if I take Q, we have to define an operation, call it a plus operation or an addition operation on these 2 points, such that it also lies on EFP, that is, it should be closed, right, and the following relations also has to hold for all P, Q and R which lies on E of Fp. So, what are the fundamental requirements? The first thing is the commutativity property, that is, we know that if I add P and Q, this should be the same as adding Q and P. Okay. It also should satisfy the property of associativity, which means that if I take P plus Q and then I add R, it is the same as doing P and adding it to the sum of Q and R. Okay. That is, it does not matter in which order we are doing the addition operation. Similarly, there should be an identity element, that is, if I take P and if I add O, then I should get back, and it is the same as O plus P because of the commutativity property, and both of them should actually go back to P, that is, there O that is essentially here the identity element, okay, and O is generally referred to as the point at infinity. So, that means the point at infinity is assumed to be the identity element in the plus operation that we are trying to define here. Similarly, another point is that there exists a minus P, such that if I take P and I add minus P, that is the additive inverse of P, then I should get back O, that is the point at infinity again. Okay. So, therefore, minus P is the additive inverse of P. So, let us try to see how we can do these operations. So, consider an elliptic curve y square equal to x cube minus x plus 1. So, this is the form of an elliptic curve that we have chosen here. So, if P1 and P2 are 2 points on this curve, so consider that there is another point called P2, and let us try to define an addition operation on P1 and P2. Okay. So, what we essentially expect by the Diophantous technique is that if I take P1 and P2 and draw a straight line through this, it should intersect the elliptic curve on a third point, like. So, this is the same thing which what we have seen in context to solving the first puzzle that we started with, right. So, now for our addition purpose, instead we do not take this as the sum, but we take the reflection of the point of this point on the x axis as the sum, that is, we call P3 to be the sum of P1 and P2. So, we take P1 and P2, and remember that what we started with was taking 0 0 and 1 1, and it intersected the curve at a point half half, and instead of taking half half, we actually took the point of half minus half. Okay. So, this has got a very close relationship with the Diophantous technique, right. So, we take this point and we draw this line. So, now we will try to make it more formal. So, therefore, immediately you understand that if I tell that P3 is a sum of P1 and P2, then we can actually obtain the ordinates of P1 plus P2 by using the techniques of coordinate geometry. So, that actually motivates us to apply coordinate geometric techniques here. So, consider that there is a point P and there is a point Q, and the point P at Q and Q have got the ordinates as shown in the diagram as x1 comma y1 and x2 comma y2. So, what we are telling here is that we have got say a curve, okay, and this curve has got 2 points. So, one point is P, the other point is Q, and we are considering this line, that is the sum of P and Q. So, P, the ordinate of P is x1 comma y1 and the ordinate of Q is x2 comma y2, and it is intersecting the curve again at a third point. So, call it minus P plus Q, because we will consider the reflection of this point on the x axis as the sum of P plus Q. So, therefore, this point is the point R, which is the sum of P and Q. So, what we do is that we actually consider the slope of this line first, that is consider the slope of this particular line, which is actually used to join this P and Q. So, therefore, call this line as some line like y equal to mx plus c. Okay. So, what is the value of y here, of m here, which is the slope? M is immediately obtained as y2 minus y1 divided by x2 minus x1. Okay. So, therefore, of course, here when we are writing the m like this, we are making an assumption that x1 and x2 are not the same. Okay. So, under these assumptions, we know that we can write the value of m like this. Okay. So, now we will try to find out the intersection of this line with the cubic equation. Okay. So, we started with the cubic form, and the equation of the curve is like y square equal to x cube plus ax plus b. Okay. So, what we do is that we take this and we substitute this, that is we take y2 as m into x2 minus x1 plus y1. So, that is straight away from the equation. So, we know that if in this equation, if there is a point which has got a coordinate of x or ordinate of x, then the y ordinate is obtained by this, right. So, therefore, if we substitute x here, this is the corresponding ordinate for y. Okay. So, we can take this y and substitute this in the equation, right. So, that means that we can actually take this and we can combine these two equations and we can write them as m x minus x1 plus y1 whole square is equal to x cube plus ax plus b, right. We can write them in this form, and therefore, we can actually rearrange them and we can write them as 0 equal to x cube minus m square x square plus some more terms which we are not actually bothered with. So, again you see that there is a very close similarity with the Diophantous method, right, because what we are now doing is that we know that there are 2 points x1 and x2, and the third sum, if I believe it to be x, right, is if I add these two things I get m square. So, that means that x is nothing but m square minus x1 plus x2, right. So, if I know that this particular curve is satisfied by 3 x values because of the cubic thing, right. So, 2 of them are x1 and x2, the third point if it is x, then if I add them, then it is nothing but the minus of minus m square, which is m square. So, that means x is nothing but m square minus x1 plus x2, right. So, we take this x and that is by my essentially the ordinate of the third point of minus p plus q. Okay. So, that is the way, I mean, so therefore, we know that if we can obtain this point, similarly we can obtain the x coordinate of this one also, because it is the same, right. The x axis is it is, since we are taking a reflection here, this point's x value and this point's x value are the same x values. So, therefore, the x is given by this m square minus x1 plus x2, where m is actually obtained by this equation. Okay. So, if we combine this, this will essentially look like this, that is okay, I will come to this actually later on, I mean the combined form, when we summarize the results. Now, the obvious question is, what about the case when p and q are actually the same points? That is, if the point p and q are actually the same point, then we cannot write an m value like this, right. So, the obvious answer to this is, since we are drawing a tangent here, we do a differentiation there, right. We differentiate the value of y with respect to x to obtain the corresponding equation of the tangent. Okay. So, what we do is that we take this line, that is y square equal to x cube plus ax plus b, which is the equation of the curve, and we draw a line. Like what we do is that we take a line and write 2y dy by dx is nothing but 3x square plus a, right. So, therefore, dy by dx at any point x1 comma y1 is defined as 3x1 squared plus a divided by 2 of y1. That means that if I take this equation of the curve here, then if I draw a tangent here and the tangent is defined at the point of x1 comma y1, then this is the slope which we are defining here, right. So, therefore, this becomes the slope of this tangent, right. So, therefore, now the question is, that is how do I actually obtain the third point. So, therefore, after this we can do a similar technique as what we have seen previously, and we can actually obtain the ordinate of the third point, right. So, what we do is that we again assume that this particular equation y equal to mx is substituted into the curve equation, okay, and we again solve for the 3 point sum, and we obtain the ordinate of the third point. So, in this case, if I do so, then again I get this form like 0 equal to x cube minus m square x square plus so on. So, therefore, in this case the 2 points, that is x plus x, if I take that this point is x1 comma y1. So, it is 2x1 actually, x1 plus x1 plus the third point is x sums to m square, like what we have seen previously. So, that means that x is nothing but m square minus twice of x1, where m is actually obtained by 3x1 square plus a divided by 2y1, right. So, therefore, this is the way how we can actually obtain the value of x, and similarly again we can draw a reflection of this point and obtain the corresponding sum point, right, of the same x and y. So, actually this particular way of obtaining the third point is called as a doubling of 2 points. Okay. So, this is actually commonly called as a doubling, this particular operation, whereas this is called commonly as the addition operation or the point addition operation. Okay. And these actually forms two fundamental operations of the elliptic curve cryptography. So, now we again have this question, like what happens when P2 is equal to the point at infinity, then what happens. So, that means that what we are saying here is that we will take P1 and the second point is the point at infinity. So, we basically what we do is that we take P1 and we draw a vertical line through P1, and therefore, it intersects the P1 at the third point. So, what we need to do after this is we need to reflect this point, and if I reflect this point, then we get back the value of P1. So, therefore, this actually means that the point at infinity satisfies or rather behaves as the it behaves as what the group property would want it to satisfy, right. That is, O is essentially serving as your inverse, because you are adding P1 to O and you are getting back the value of P1. Okay. So, therefore, this means that the point at infinity, with the additional point at infinity, we are actually ensuring that the points on the elliptic curve satisfies the group properties. So, actually there is a so what we fundamentally require is these 4 properties. We need that it should essentially satisfy the property of commutativity. This follows from the way the addition has been done, because if I draw 2 lines, it does not matter which way you are drawing it. Similarly, the point or rather the existence of an identity element is also understood by the way what we saw just now. Similarly, the point inverse is also understood, because if you take P and minus P, it will again intersect the point at infinity. If you reflect that point at infinity, you still get back infinity, because it is assumed that the point at infinity exists both at the top and both at the bottom, right. But what is not so obvious is this associativity, why it is associative also. But this is actually a quite lengthy proof, and it is actually beyond the scope of this discussion. So, therefore, we will assume that it also satisfies the acidity property, and therefore the elliptic curve elements actually, the elliptic curve points satisfies the group properties, or rather forms a group, forms an abelian group under the addition operation. And how is the addition operation defined? Now we take 2 points and we draw a straight line through it, intersect it at a third point, reflect that point on the x axis to obtain the corresponding sum, or if the point P and Q are the same, then we draw a tangent through that point, again obtain the point of intersection, reflect that and obtain the corresponding output. So that is the corresponding, either how we do a P plus Q where P and Q are different, or we do a 2P, or that is how we do the addition operation, or how we do the doubling operation. So that is how it is defined. Okay, so therefore this is a summary of what we have seen, that is if the points are different, that is if I take 2 points like x1 comma y1 and x2 comma y2 in the elliptic curve, then your slope is defined like this, where x1 and x2 are not the same, but if x1 and x2 are indeed the same, then this is the way the slope is defined. And for both these cases, your third point is actually lambda square minus x1 minus x2, and the corresponding y ordinate is obtained like this. Okay, so therefore you just take this and you substitute this and obtain the corresponding y sum. So this is a pictographic description of, you take P and Q, you add it, it intersects at the third point R, you again reflect that point to obtain the corresponding R. So therefore you can actually engage coordinate geometry to do this operation. Similarly for other cases like this. Okay. So this is a case of a doubling operation, like we take a P point and we want to do a 2P operation. So what we have done is that we have considered a tangent at this point, it intersects at a point R, we have reflected it to obtain the corresponding sum value. Okay. So therefore this can be similarly performed. So this is again like doing P plus minus P. So therefore you take P and you add with this additive inverse minus P, it intersects at the point at infinity, and the point at infinity is, if we again reflect this, we again obtain point at infinity. So as a result of the above cases, you have got this property. So O is called the additive identity of the elliptic curve group, okay, and hence all the elliptic curves have an additive identity O. So now we will come to the concluding part of this, that is discussing about projective coordinates. Now we shall see in our next class that when we discuss that when we are actually talking about the scalar operations, then what we essentially need to perform is repeated additions and repeated doubling. Now because of this, we essentially if we try to understand the elliptic curve operations, then the underlying we have actually to perform the finite field arithmetic operations, like we have to either perform finite field multiplication, finite field addition, finite field inverses, and such kind of operations. So therefore if you want to make our implementations efficient, which is also very important, it is important that the underlying field operations needs to be done in a clever way, that is we need to minimize the underlying field operations. So one of the most complex underlying field operations is the multiplicative inverse. So therefore it is always an objective of how, when we are implementing a finite elliptic curve scalar multiplication, okay, is actually by repeatedly reducing the number of inverses. Now what is scalar multiplication is like, is defined like this, that is see, consider a scalar quantity which is defined as lambda. Okay. So what we are interested in is in performing, so we consider a point or base point P, okay, and we are interested in computing lambda P. Okay, that is we need to multiply this P with the scalar quantity called lambda. So that essentially we know that we can do it by doing P plus P and so on lambda number of times, that is we can perform this addition lambda number of times. That means if I take or start with an elliptic curve and I take another point P, then the first thing which I have to do is P plus P. So that means I need to draw a tangent through this and this intersects the curve at a point, we take its deflection, this becomes twice p. So, now we take this and we want to add this with further p. So, that means that I take this and I again intersect this line with this point p, this again intersects the curve at a third point, we again take its deflection. So, that becomes 3 p, right. So, we continue this process, right, that is we perform repeated additions or repeated doublings and additions to compute the value of lambda p. Now, there is, I mean, we can actually do it in a efficient way, like by as we have seen in the case of raising a value to its exponent, we have used the square and multiply in order to do it efficiently. Similarly, here we can actually engage a double and addition algorithm to do this efficiently, but that we will see in the next class. But what is important to understand is that when you are doing this p plus p or p plus a third point, a different point, then underlying operations which you are doing actually encompasses finite field multipliers, finite field inverses, and so on. So, what is important is that when you are doing this operation, it is to reduce the cumbersome operations, right. So, what we will try is, if we consider that the underlying finite field operations, because elliptic curve is always defined on a finite field, right, in this case. So, therefore, the underlying finite field operations are inverses, multipliers, and additions. So, if we assume that this is the most cumbersome operation, then our objective will be to reduce these inverse operations as much as possible. So, in order to do that, there is a very effective transformation of the elliptic curves, which is from the affine coordinates, that what we have seen, into a coordinate system which is called the projective coordinate systems, which is actually very helpful in reducing the number of inverse operations. So, what we do here in this projective coordinate system is that instead of considering a point like x comma y, we actually elaborate this and consider a point as to be made up of 3 important components, that is x, y, and z. Okay. So, it is assumed that various points, okay, which are actually lying on the curve are, instead of having 2 ordinates, have got 3 ordinates x, y, and z. And this transformation from the affine coordinates to these projective coordinates. So, what we first do is that we take the affine coordinates, transform it into the projective coordinates, perform all the operations in the projective coordinates, and then finally again bring it back to the affine coordinates. Now, what has been seen is that in this process, the number of inverses gets completely removed. That is, when you are doing your addition and doubling operation in the projective coordinate system, then it is completely devoid of the multiplicative inverse. It is made of multiplications are required, but there are no multiplicative inverses which are employed here. But of course, when you are doing this final transformation back into the affine coordinate, you require to do one finite field inverse operation at that point. That means that the entire purpose or entire efficiency of this coordinate system transformation is that we are actually reducing the number of multiplicative inverses at the cost of some extra multiplication operations. So, therefore, more formally this looks like this, that is, the 2-dimensional projective space over K is given by the equivalence class of triples x y comma z with x y z in K, and at least one of where at least one of this x y z is non-zero. Okay. So, therefore, this essentially is actually made up of equivalence classes. So, x y z, these are the 3 points, and they are actually equivalent when under certain conditions, that is with x y z in K and at least one of the x y z being non-zero. Now, when do we say that 2 points like x1, y1, z1 and x2, y2, z2 are equivalent? We say 2 triples like this to be equivalent if there exists a non-zero element lambda which is also in K, such that x1, y1 and z1 is equal to lambda x2 into lambda y2 into lambda z2. That is, if I take x2, y2 and z2 and multiply each of them by lambda, I get the second point. Okay. So, therefore, it is also commonly referred, or this equivalence class is actually defined only by the ratio of x, y and z. Okay. And therefore, it is also commonly referred or written as x is to y is to z, which indicates that we are actually interested in the ratio of the x ordinate, y ordinate and the z ordinate. Okay. So, therefore, all such triples where this ratio is maintained are actually believed to belong to one particular equivalence class. Okay, if there is another point which also maintains a ratio, then that belongs to another equivalence class. So similarly, you can actually divide your entire coordinate system or other entire set of points into equivalence classes. Okay, so that's how it's defined. So for example, I mean continuing further, like if z is not equal to 0, then you can always write x is to y is to z as same as that of x by z is to y by z is to 1, because that also maintains the same ratio, right. Your x is to y is to z here and here are the same. But what about the point at z equal to 0? Then you cannot write like this, right. So therefore it is, we obtain, so we say that this is the point at infinity. So we obtain the point at infinity if we do like that. So therefore the two dimensional affine plane, so what we have seen previously was this, that is x comma y was the corresponding affine plane, and that we defined, and x also belongs to k and y also belongs to k. So therefore the ordered pair x comma y is a subset of the Cartesian product of k and k, right. Now if we use a transformation like this, where we transform this x and y to x is to y is to 1, then actually this gets transformed into the projective coordinate system. That means what we are trying to say here is that the ak square and the pk square, both of them are actually, you can actually define a one to one relationship, right. You can transform any element here into this, and you can actually take any element here and convert it back into the affine space. Okay. Now there are some advantages, as I told you, is that with projective coordinates, which we will see in the next class also, there are certain distinct advantages of using projective coordinates. That is, it reduces the number of inverse operations which are required from the implementation point of view. Okay, that is, for example, if you see these operations, like when we have considered these equations, then instead of when we are performing this, right, that is all of them are finite field elements. So therefore we need finite field squarers, we need finite field multipliers, we need finite field division operation, which is nothing but based on finite field inverse operations. So the objective of transforming this into the projective space and then performing operations is to reduce the number of, basically it is to reduce the number of multiplicative inverses. Okay. So that is the objective of why, I mean, one of the important advantages of transforming a elliptic curve system into projective coordinates and performing the operations in the projective space. So I will like to just make some comments about the singularity of an elliptic curve. So for an elliptic curve y square equal to fx, where we can actually find out the singularity in this fashion, that is, we actually rewrite the equation as fx comma y is equal to y square minus fx, and a singularity of the elliptic curve is a point x0 comma y0 such that your delta f delta x and delta f delta y are the same. Okay. So we actually find out delta f delta x with respect, so we basically differentiate this curve y square minus fx with respect to x. Okay. So if we do so, then we actually obtain, so we can actually do that. Similarly, we also differentiate with respect to with y. Okay. For example, here we differentiate, if we differentiate this with respect to y, what do we get? We get 2y, right. So we get 2y 0, because that is the point. So what we are doing is that we are just, because in that case the fx, if we differentiate this with respect to y, that is 0. Okay. So therefore we get 2y 0, and the other thing is fx 0 minus fx 0. So what we are doing is this, that is, we are taking the curve fx comma y, and that is equal to y square minus f of x, and we are differentiating del f with respect to del x. So del f with respect to del x will be equal to 2y0. Okay. Similarly, your del f with respect to, del f with respect to del y, del f with respect to del x will be minus of f dash x, right. So therefore here what we are saying is that 2y0 and minus of f dash x is equal to 0 at the singularity point. Okay. So we say that 2y0 equal to minus f dash x equal to 0. Now when we are saying that 2y0 is 0, that is y0 is equal to 0, it means that y0 square is also 0, right. That means if you substitute this in this graph, right, then it means that your fx0 is also equal to 0. That means we can write that fx0 and f dash x0 both are equal to 0 here. Okay. So that's why we call this point at singularity as a double root, where it also satisfies this and also the differentiation is satisfied. Okay. So, if you draw a curve like this which has actually has got a singularity point, then you will find that it is quite distinctly different from the other elliptic curve operations. Okay. So, it may have something like this kind of edge over there, right. So, it is this point basically. So, it is usually assumed that the elliptic curve has got no singular point. Okay. So, therefore, I mean we can go through this and we can find out that if we go through this, then if we assume that f has got double roots, then if we take this x cube plus ax plus b and we for double roots, therefore, we know that we will actually equate the differentiation of this equation with respect to x, that is 3x square plus a with 0, and therefore, your x square is minus a by 3 from this equation, right. So, if you substitute this, therefore, you know that x power of 4 plus ax square plus bx is equal to 0, because that is also a root, right. So, therefore, if x cube plus ax plus b is 0, you can always multiply this by x and that is still 0, right. So, therefore, you get x power 4 plus ax square plus bx is equal to 0. If you take this and now substitute this one into this, then you get a square by 9 minus a square by 3 plus bx is equal to 0, and therefore, x is equal to 2a square by 9b. So, now if you take this value of x and substitute back into this equation of 3x square plus a equal to 0, then you get that this equation which is called as 4a cube plus 27b square is equal to 0. Now, this is commonly referred to as the discriminant of an elliptic curve. That is what we have seen in quadratic equations, we know that when the discriminant is 0, then the two roots are same. Similarly, in cubic curves, when f has got double roots for the singularity conditions, then it satisfies 4a cube plus 27b square is also is equal to 0. So, this we can prove in a slightly different way also. But I mean, one of the very important curve equations is for characteristic 2 and it is useful for implementations. So, we can consider again the Weierstrass equation, and depending upon the facts, right, we can actually again modify and we can actually reduce it into various forms. Like one of the various very common forms is again y square equal to x cube plus ax plus b. So, I am not going into these detailed reductions, but it can also be done in the similar fashion as we have seen for the other characteristic. Now, I will just throw some points to think on, like we have thought about the discriminant point. So, you see that suppose that the cubic polynomial this is factored as this, then we can actually show that 4a cube plus 27b square is equal to 0 if and only if 2 or more of the E1, E2 and E3 are the same. So, you can actually reduce both the curve equations and this one and compare the coefficients. If you simplify, you will again get back this equation. So, this is another way of proving the discriminant. That is, if two roots are same, then you get this equation to be satisfied. Okay. The other thing is that you can sketch these two curves and you can note that the second curve E2 is actually not an elliptic curve because it has a singular point. So, if you do this, you will get a feel about the singular point, the singularity of the curve. Okay. So, we stop at this point, and these are some of the references that I have used in my video. So, I have used the Stinson's book and the Washington's book and also this book, and in next day we can actually discuss about the applications of elliptic curves to cryptography.